Hello everyone, let's talk about another hard problem on Leetcode today. Minimum number of days to disconnect island, Leetcode 1568. In this problem, we are given an m into n binary grid where 1 represents land and 0 represents water. So, then an island is a maximal 4-directionally horizontal or vertical connected group of ones. So, this means that islands are not diagonally connected. The grid is said to be connected if we have exactly one island, otherwise, it is said to be disconnected. In one day, we are allowed to change any single land cell containing 1 into water cell containing 0. Then we have to return minimum number of days to disconnect the grid. Then they have given some examples as well. In example 1, we are given a binary matrix like this, where island is colored as orange and water is colored as blue. Then on day 1, we sync this land cell and now we get a 0, but the island is still connected as L, right? And on day 2, then we sync this land cell as well. So now the island is disconnected. We have one island like this and another one like this. So that is why we require 2 days to disconnect this grid. Similarly, in example 2, let's sync this land cell on day 1, but we still have one connected grid. And then we again sync this land cell as well. And now we have no island, and that also means no connected grid as well. So we will return 2 in this case. Now, in terms of solution, initially I was thinking of using union find algorithm. And initially when I was trying to solve this problem, I was thinking this problem is connected to disjoint set or union find algorithm because I can quickly find out if island is connected or not using union find data structure. But the problem is not just about connectivity. We have to also sync the land cells and then check the connectivity. So the harder part is to dynamically sync the land cells such that we can find out after removing some specific cells if the island is now disconnected or not. And this is what will require a lot of computation. So then I thought that maybe this problem is connected to articulation point, and an articulation point in a graph is a vertex or cell in this context of the grid that when removed increases the number of connected components in the graph. And this concept can actually be useful in this problem for the case when removing a single land cell will disconnect the grid, and in that case we can return the answer as 1, but it will not cover all the cases. For example, what if graph is resilient and it doesn't have such articulation point or single point of failure? And this is where an interesting observation comes in. So the main idea of the problem is that the number of days to disconnect an island is always less than or equal to 2. And we will come back to why that is the case in a minute. So then our problem has only 3 possible cases. Case 1 is that we have the number of days as 0. And this can happen if the grid has no land cell, for example, grid on the left, or we have more than one island, like the islands on the right side of the diagram. Then the island is already disconnected. So in this case, we will return number of days as 0. Then in case 2, we will have number of days as 1. And this will happen only when the graph has an articulation point. So for example, take the graph like this, which has this node, which is a single point of failure. So if we remove it, the graph is now disconnected. Similarly, if we have a grid like this, we can see that this node is like a single point of failure. So it is an articulation point. And if we remove it, now we will have 2 connected components. So to sync an articulation point, number of days is equal to 1. And now we come to an interesting case, that is case 3, where number of days will be equal to 2. And the reason for this is the grid structure is such that it will take 2 days to disconnect the grid. So let's look at this example. This is how our graph looks. And now if we sync the cells 6 and 8, then this is how our 2 edges will be disconnected. And now we can see that node 9 is disconnected from rest of the island. So because we sank land cells 6 and 8, in this case, we will return number of days equal to 2. So no matter how big the grid size we take, there will always exist a node such that it will already have water on the 2 sides of it. So if we break down the cell or if we sync the cell on the remaining 2 sides of it, then this node will be disconnected. And this is the main observation for this problem. So to sum up, if we are in case 3, that is we couldn't find articulation point or the graph was already not disconnected, then there will always exist a vertex such that it will already have water on the 2 sides. For example, sum shown here. And in this case, if we chop off 2 connecting edges with the island, then this node will be disconnected. And this is why number of days will be equal to 2. And such graphs are called biconnected graphs. And the definition for this is that the graph should be connected And second thing is it should not have any articulation point. And if the graph is bi-connected, then in this case we have to remove multiple vertices to make graph disconnected. And our grid is, or our island is a special case here, as we will always find some vertex which can easily be disconnected by rest of the graph by removing two edges. And coming up with this intuition is hard, and this is why this problem is also hard, and this is what I learned in this problem. And once we have understood these three cases, this is how our algorithm will be. In step 1, we will check if our graph is already disconnected or there is no island, then we will return 0. This can be done just by writing a DFS code and checking if our graph is connected or not. If we have passed step 1, then we come to step 2. Step 2 will be to check if removing one land cell will disconnect the grid immediately. In this case, what we can do is we can actually go through each land cell, temporarily sync it, and check if removing that point actually breaks the connectivity of the graph. And such point will be an articulation point in the graph. And if we find it, then we will return number of days equal to 1. And we can actually reuse the isConnected function from step 1 to check if the graph is connected or not after syncing the cells. Another approach can be that we can also use Tarjan's algorithm to find the articulation point. And if there exists one articulation point, then we will return a number of days equal to 1. And finally, step 3 is if case 1 and case 2 don't apply, then number of days is equal to 2. And because this graph is bi-connected, and the grid structure was such that we will be able to disconnect the graph in 2 days. And now let's jump into the code part. Let's first write the structure of min days. If graph is not connected already, then we will return 0 here. But if graph is connected, we will check if there exists articulation point in the graph. So the way we will do is we will just sync the land cell and see if the graph is still connected. If not, then we will return number of days equal to 1. So if this current grid cell is a landmass or land cell, then we will sync it temporarily, of course, and check if graph is still connected. Instead of returning 0, now we will just return 1 if it is not connected. And if it was not the case, then we will bring back the landmass from water by setting it equal to 1. And finally, if we have reached here, then we are at case 3. So we will return 2. And now let's write our isConnected function. So we will again get our m and n. And now we will run the DFS to check if the graph is connected or not. So what we will do is we will create a visited set for this grid. And again, we will run the same two for loops. So I can just copy paste it here. So if grid ij is a landmass, then we will start the DFS from this point, right? What I can also do is I can extract it out as a getStart function, which will return the starting point of the islet from where we will start the DFS. We can name this function findStart, for example. And now we will run the loop on the grid. And whenever we find a first landmass, we will return its index. Otherwise, if we couldn't find such land cell, then we will just return null. So we can just say, give me the start point of the island. And if start is equal to null, that means there was no island. So this graph is not connected. So we will just return false in this case. Otherwise, now we will start our DFS from the starting point using the visited set. And after doing the DFS, again, I can just copy paste this code. So again, we will just run the loop. So if this is a land cell and if it is not present in the visited, that means this land cell was not reachable from our start point when we found the start point of the graph. So that means this graph is disconnected and we should return false in this case. And once this is done, if we have reached the end, that means we can return true. Now let's define the DFS function as well. In DFS, we will mark the land cell as visited if it is reachable from our starting node. And we can just pass in the boolean visited set. We can pass the row and the column from where we start the DFS. So if first thing we check is the boundary condition, if row is less than 0 or row is more than grid.length or C is less than 0 or C is more than grid.length, sorry, grid0.length, or if we have already visited this node, or if this is not a land cell, then let's cut short our DFS trip and return. Otherwise, we will just mark this cell as visited because it looks like a valid land cell. and we have to traverse to adjacent land cells. We have to run like 4 directional DFS, right? So let's define the directions as well. So generally we will define a 2-dimensional directions array. So this is for going up, this is for going down, this is for going to left, and this is for going to right. So now we have the directions array. So then we can just loop on it and we will get the new row as r plus whichever direction we have chosen and the x coordinate of it. Similarly for column, it will be column plus the corresponding column index in the direction. And once we do this, we can actually call the DFS with this new row and column. And eventually we will have the visited array based on it. And finally, when the DFS completes, we will have the visited set containing rows and columns reachable from the start node. And if any land cell is not present in the visited set, that means this island is disconnected. So this was disconnected function. Now let's run this code. Oh, looks like a copy paste error. I should be using grid.length and grid0.length instead of m and n. We had 2 errors, right? I hope these are the only ones. Let's run the code again. Okay, there's an index out of bound. Because I should also use equality here. My bad. So I think this should fix it now. Yes, let's submit this code. Cool. In terms of time complexity, we can see that it's connected takes O of m into n time to find start, and then this whole DFS also takes O of m into n time because we are just going deeper and deeper on all the land cells, and at maximum all the land cell will be equal to m into n in terms of size. But we are running this m into n loop to sync those land cells, and then for each sunk land cell, we are actually checking if this island is still connected or not, and that takes O of m into n time again. So for all the sunk land cells, it will be O of m into n square in terms of time complexity. And in terms of space complexity, it will be O of m into n because of this DFS recursion stack. And second thing is this extra visited array that we are using. So that's it for today. I hope this video was useful to you. If it was, please like and subscribe. The code link is in the description below. Have a nice time. Thank you.